let's get started with chapter 13. Let's see how I go. I'll try to cover 13a and b, which are pretty long. So introductions to dynamics. First thing is we need to use a model of a particle. So any object will be independently of their size and weight will be narrowed down to a single point on as a moving or stationary object, meaning that its size. Let me turn on my. Do I need a pen or laser? Probably a pen. Okay. So its size and the rotation of the object itself is ignored. If you continue with its application in physics or further complex mathematics at university, let's say in engineering, you will have to adjust the model, meaning it might be a bit more complicated than that. Système International in terms of units, or MKS, stands for length is in meters, mass is in kilogram, and time will be in second. Vectors versus scalar, as we're going to use into multi-dimension motion, so 2 to 3 dimension. And moving on to forces, 1 Newton is equivalent to 1 kilogram weight, and 1 kilogram weight is 1 kilo, the mass times the Earth acceleration, which is 9.81 or sometimes 10 meters per second per second. Alright, first concept is direct application of vectors. A resultant vector is made up of a sum of vectors, which is what we learned before, applied to forces that are exerting on a particle. First is a force is a vector quantity, so it has a magnitude and a direction, and the vector sum of the forces acting on a point is called the resultant force. So for a stationary object, you have I'm sitting here, I have a downwards force of due to the Earth gravity, and later on we look at the third Newton's law. There is an opposite force acting on me from the chair that is preventing me from falling down. So in my situation, if I am myself the particle that has the forces exerted on me, the resultant force is actually 0, or the null vector. Application, so you have your Cartesian plane with your unit vectors associated with. You have 4 vectors with respective magnitudes. Pause the video, try to find the resultant force, and then determine its magnitude as well as the angle to the x-axis or the I direction. Alright, so what you should do for each of those vectors before you do the resultant force is 5 Newton is 5I, that will be your negative 2I. Here is your positive 3J, and here is your negative 2J. You combine them and simplify, that gives you 3I plus 1J for the resultant force. I'm a little bit suspicious about that n as a unit. I know it's in newtons, but it's kind of inconsistent with the vector notation. Anyway, that n actually should be here for sure. Okay, so to find, you have your vector here. You determine the magnitude doing the modulus or apply Pythagoras, that gives you square root of 10, specify the units. To find the angle to the x-axis, which is your theta here. You have your right angle triangle, so you do tangent of theta is your opposite over your adjacent. So here you have 1 and here 3, both positive, so that gives you 1 over 3. You use your CAS to do the inverse tangent of 1 over 3, and that's your angle. Make sure your calculator is set in degrees. If it's set in radians, as long as you specify the units, you should be fine. Okay, it's going to be annoying for an examiner as they will have probably the answer in degrees, but they should be able to do the conversion. Alright, as a general approach, when you have a force, a vector force, and you want to do the resolution in a given direction, you break it down into two components, A and B, and you can see on the diagram, the vector A will be parallel to the direction you want to project to, and your vector B will be perpendicular. So A and B will be perpendicular, vector A will be in the direction. If you know the angle theta from which you want to project towards to, your component A, its magnitude will be the, let's say you know two things. Hang on, let me annotate here. So you know your angle, which you want to project, and you also know the magnitude of the vector or the force that you apply. Once you know those two, you can find the magnitude when you project along the A vector, which is P times cos of theta, and the perpendicular one is going to be P times sine of theta. Very handy to remember those calculations. You don't want to have to demonstrate every time, and it will save you time on the long run. Okay. Later on, you'll find out. Do remember that in that theta, because that angle you will project towards OX, but that line that is horizontal, later on we apply it to inclined plane, and as it won't be horizontal, you just will use the same notation to project it. So the resolved part of the force of P Newton, so P is the magnitude in the direction which makes an angle theta, so theta is what we know, P is the amount, with its own line of action is a force of magnitude, P of cos theta, which is what we did here earlier. So it's in the direction of, where is it? So its own line of action will be A, or unit vector A, which is what corresponds to the question. Okay. Alright. Now, that example is the same as kind of before. It's the same concept. What you want to find out is the vector projection, but now you don't know the angle in between. You have a vector form, you can determine the magnitude, so differently from before we knew the angle and the magnitude. Here we have the vector forms in terms of I and J, and we know the vector A in which you want to be project towards is in the vector form as well. You will need to do the scalar or dot product and determine your unit vectors. So starting with your vector A is 2i minus j. Find your unit vector, so you just divide by the modulus. So the modulus of that will be square root of 5. So you have your 1 over square root of 5. So that's my unit vector. Alright. And to find the projection, we're going to use that unit vector again over here. And then the second step is going to be up here. I can't see my cursor. Hold on. You do the dot product between the two vectors, F and A. factor 1 over square root of 2, it's a scalar amount. So you end up with that scalar value that you will use as a factor for your projected vector. Simplify it, and I will give you your vector projection. This is going to be parallel to our vector A, and it will have a if you knew the angle, this is the same as P will be the actual magnitude of the vector of the force F, and if you knew the angle, P cos of theta will be the magnitude of that. Okay, and then you will write that sentence if that makes sense. Well, let me change color because really it's hard to see. Alright, next situation, you have three vectors. Find the magnitude of the resultant force. So first is you will find the resultant force as a vector form, and then you extract the modulus, and with the direction of the resultant force, you will just need to you have the magnitude for part A. Determine the angle to the 5 Newton force as it is the horizontal. So we're going back to the original situation, which is this one. So you will know the magnitude from part A, and the angle is given from the graph. Okay, so for the horizontal one, it will not be difficult. For the 2 and 3 that make up an angle of, this one will be 30 degrees. For that one will be 15 plus 30, that's 45 degrees. What you will do is you project those, so horizontally you will have the 5 plus the 3 cos of 30 degrees plus 2 times cos of the 30 plus 15 degrees. Vertically you will only have the 2 and 3. 2 and 3 will be the magnitude, also the hypotenuse of those respective right angle triangles. So it will be, see how I have 2 cos of 45 degrees. The y component will be 2 sine of 45 degrees. So that's the slight difference. You just use cos for the horizontal and sine for the vertical. So now we have the two components of our resultant force, and which we have here. Okay, so they evaluate to 2 decimal places each components, and then they use Pythagoras to find the actual magnitude. To be a little bit more precise, I will keep the estimate from the CAS calculator on screen to reuse that, and then to find the hang on, let me refresh. So we want to find the direction, so we want to find the angle, so we need to find the angle, so we need to keep those again, this is the wrong color, so let me change it to red. I'm going to use my laser pointer. So we have our x component and our y component, and to find the direction, what we do is the ratio of it, that gives us our tangent. We do the inverse tangent and use the CAS to determine that angle, and that gives us on the graph, you can annotate here, that will be the angle of the resultant force, and that's the magnitude from part A. You can also, they also constructed the sum of the vectors. So you have those three vectors. You make a choice. Let's say we start with 2, which is 45 degrees. We had to add the tail to the first vector and so on. So 3 with 30 degrees, and 5 horizontally. And if it was scaled, you could, using a protractor, that would be given the angles, and measuring the length of that will be should be the same if it was a scaled diagram. Alright, let's move on to 13b. Pretty long chapter. We introduce a few new concepts applied to dynamics, and we move on to the 3 Newton laws, and with some application. Alright, first thing is, in weight, on the contrary to what we talk in real life, it is a force. It needs to be expressed in Newton, and its definition as a force is the mass times the acceleration of where we actually measuring the weight. So most of the time we'll be on the Earth, and g will be approximately, it's about 10 meters per second. Okay, usually they will give you the value, and it's a nice approximation. So let's say you have a mass of 80 kilos. So 80 kilos multiplied by 10, that's 800. This is the weight. My weight is actually 800 Newton. That's what the Earth exerts on me as a force. Okay. Next is the momentum. The momentum is the mass times the velocity. Mass is a scalar amount. Velocity is actually a vector, so the momentum is also a vector. It will have the same direction as the velocity. The units, simple product. Mass is in kilogram, velocity is in meters per second, so that is the unit. Usually what's interesting is the change of momentum, so which is the difference between the initial and final momentum, and it has a linear relationship with the force exerted to the object. Okay, so direct application. Find the momentum of a particle. So you will take straight away vector velocity, you multiply by the mass. Direct application. Here it's a vector form. The next one is linear, so it's in easterly direction, so it gives you the magnitude, and you just do either a product of a vector by a scalar, or a product of the two amounts, and you indicate the direction. Here we need to find the change of momentum, so apply directly the momentum using the initial velocity, which is 5. It's slowing down, so the final momentum will be that amount. You do a difference that gives you a negative amount. Don't forget the units. Alright, let's start with the first one. Is the first law of motion, which is a particular situation of the second law, which I prefer, because the second law is actually absorb the first and the second law itself. So if you have a particle that is either stationary or it's moving at a uniform straight line, means it's a constant velocity. So straight means it doesn't change any direction. That makes sense. And uniform is the vector velocity is not a function, it's a constant. Well, it's a function but independent of time. So unless you have another external forces, the resultant force is a null vector or is 0. It's a null vector because the force is a vector. Okay. So what it implies is you need to apply a force to make the object to start moving or to stop it. So moving is, you assume it's stationary, or if it's moving at a uniform at a constant velocity, you will need to apply force to stop it. That's the respective situation. But once it's moving, then it will move at a constant velocity without any force being needed. Okay. If an object or a particle is at rest, hold on, just give me a sec. So if the object is either stationary or it's moving at a constant velocity, then you can conclude that the resultant force is zero. Then if the motion is changing, then the resultant force is this time the opposite, is non-zero. Okay. All right. Just hold on. All right. Back to the first one. Hold on. So let's say the object is stationary. The resultant force is zero. Now, if you introduce a force, the resultant force is changing. So it will start moving, but then as the resultant force go back to zero, it will maintain its constant velocity. I think that's the idea here for that first dot point. Alright, the second law of motion, and I prefer that version of it, and I'll explain you in a second. So if you have a resultant force, which is again a vector, so it's going to be a sum of applying forces to the particle. If it's not zero, what you can say is that resultant force is equal to the way it works. Okay, so the way it's phrased is, it moves in such a way that the rate of change of its momentum, and that's the rate of change of this momentum. So remember, the momentum is the mass times the vector velocity, but the d over dt implies it's a rate of change. So that is the section with the rate of change, will be at any instant proportional to the resultant force. So it is proportional, and that equals to the resultant force. Okay? So that proportionality, it's for the resultant force in terms of the rate of change. If we make the resultant force the subject of that expression, this is the way we can express it. But that rate of change is also, we assume the mass is unchanged, is constant. We can take that mass out, and that is defined the actual acceleration, because the rate of change of velocity is our acceleration. So the resultant force is equal to the mass times the acceleration. Alright? Now, if the resultant force, this part, is equal to 0, then what it implies is the acceleration is 0. If your acceleration is 0, it's a constant velocity, and we're going back to the first law of motion. So the second law is a general situation. If we make the resultant force equal 0, it will it's a specific situation that is defined as the first law. So let's look at some application. You have a mass, you have a force. What will be the acceleration? It's just linear, one direction, so you don't have to worry about. Just calculate the scalar amount. So you apply the formula. So you know your mass is converted into kilograms. You multiply by g. Just give me a second. What did they do here? So okay, 60 it's not G, sorry, it's actually grams. So 16 grams converted in kilograms, that's our mass. We multiply by our acceleration. Left hand side is the resulting force, or the unique force of 0.6 Newton. We make A the subject. That gives us the amount, which is in meters per second, which will be in the same direction as the force. Alright, let's just have a look at this one, annotate the amounts, and try to give it a go. Pause the video and try to have a go at this problem. So here, don't forget the mass is in grams, so convert that into kilograms. You're decelerating over from 26 down to 24. Find the uniform force that's causing the change in velocity. Now, the uniform part of it implies that the force vector is constant, which links back to actually constant acceleration. You can use the formulas as well, but here they make it a little bit more fancy. They're going to use calculus. So we know the force is slowing down, which is retarding. So you're slowing down. It also means the acceleration is actually a negative amount. So here A is equal to K, which is a constant. We use the expression of as a function is v dv dx. We separate the variables and we'll get half of v squared equals kx plus c. So we have two unknowns. We do know at t equals 0, v equals 26, which gives us the constant amount. And then with the next situation, 35 meters later, the velocity now is lesser amount, which is 24 meters per second, which we use here. We substitute here and that gives us the k amount, which is negative, which is great. Okay, so we have a deceleration. So that's our acceleration. Then we apply the second law of Newton, which is F equals m times A. We substitute the amounts and that gives us the force. In Newton form, again, it's negative, so it's in the opposite direction of motion. Now, to answer the part, how much further could the puck travel? The trick here is, now the velocity it will get to a full stop. That gives us a velocity of equals 0. We substitute into the velocity expression. Just use that notation k and x plus c. We know the values of k and c. We make x the subject. We substitute k and c, and that gives us the amount evaluated, estimated, and which is that amount. Don't forget, hang on. X is from when the velocity is 26, so you need to subtract the 35 meters to determine the extra distance travel. This is from the starting point. Okay. All right. Here we have three vectors. F3 is unknown. We know F1 and F2. It actually gives you the acceleration, so you're going to apply the second law of motion. So you write your equation. Those are vector forms. You make F3 the subject and express all the vectors in terms of I and j and simplify. That gives you 2i plus 1j. Alright. Third law of motion. If you have a particle exert a force on the second particle, then the second particle exert a force of equal magnitude and opposite direction on A, which is what we call the reaction. So same magnitude, opposite direction. So that's why it says it's collinear, but it's in the opposite direction. So collinear, it's parallel. Opposite, it's in the opposite direction. So the idea is keep them in pairs, action and reactions, but they do act on different objects. So if you have two forces and they act on the same object, because the resultant force is equal 0, then they have either they have no motion or they will be moving at a constant velocity. Alright? So for example, if you have an object that is sitting on a table, let's say you have a book. It has a weight force going downwards, but the table has an opposite reaction, so the book will be stationary. The same is if you have an object that is moving, let's say from the left to the right at a constant velocity. So you have a car moving at a constant velocity on the road. The car will have a downwards force due to its weight, but the road will have a reaction force to the car, preventing the car from going downwards, so it will move across. So these are examples. Let's say you have an object, you have a string, you're pulling a string in the theta direction. You have no vertical motion. No vertical motion. When you apply the second law of motion, you have a reaction, but when you do the sum, that will give you a zero vertical component because you have no vertical motion. So the third law will be applied combined with the second law. Alright, look at this example with this one. So pause the video and have a go at this. Alright, so you have a lift, it's accelerating upwards. So have a drawing, you have your lift upwards is positive, so your acceleration is going to be upwards. The mass of the box is 10 kilograms. Find the reaction of the floor of the lift on the box. So the object you're looking at is the box. So on the box you have a reaction coming from the lift, which is upwards. So that's your R, which is upwards. Downwards you have the mass of the box, which is plus negative 10g, equals from the second law of Newton, law of motion, let me have the correct syntax. So it's the mass times the acceleration, which is positive 2.5. You make R the subject, and you have a reaction amount, magnitude, which is also a vector, which is positive 123 Newton, which is the magnitude. Is that what it just asking you? Okay, and it is upwards anyway because it's annotated up here. Alright, sliding friction or friction. The way you do is, let's say you have an object moving in to the right. The friction force is always in the opposite direction of the motion, and its magnitude is mu times R, and R is the vertical reaction force, which is opposite to the weight force. That coefficient mu, will depend on the surface friction. So if it's tires, it's a high friction, it's close to 1. As it's getting more slippery, let's say 2 metal surfaces, it's down to 0.1 to 0.2, so they will be much lower. If it's a smooth surface, which has the ideal situation of no friction, mu equals 0, so that friction force will be a null vector. Alright, you have a situation which is highly friction, so it's mu equals 0.3. It's horizontal, it's pushed by a horizontal force, so to the right or to the left. The convention is to the right. Look at the questions, try to resolve it, pause the video and come back to this. Alright, so first, draw your diagram with all your forces. Mass 5 kilograms, so weight force 5g. Vertical force, reaction force, you don't know what it's equal to yet, so leave it as unknown. Horizontal force is 20 newtons to the right. You'll know the duration, so keep that in mind. Your friction force is in the opposite direction, and it's mu times your reaction. Okay, so apply Newton's second law of motion. You have vertically R minus 5g, which is a weight force, and that needs to be equal 0 because there's no vertical motion. So R is equal to 5g, which we're going to substitute straight away in the next equation. Next one is 20 minus mu R is equal to 5, the mass times the acceleration. So we end up with our acceleration of A is equal to 1.06, which is a constant horizontal acceleration to the right. We multiply by 5 to find the velocity, so that gives us 5.3 meters per second. And using our constant acceleration formula, we have we can use u acceleration and the time to determine the distance traveled. And that's probably, hold on. Sorry, that was the answer for part A. So that's how far it travels. So for part B, how much does it travel further after the force is removed? So you remove the force, and what's left is those three vectors. So again, you apply Newton's second law of motion. Vertically is the same. Horizontally, you will get a new acceleration, which is negative, which is constant. You use your constant acceleration formula. You're going to use v is equal to 0 because it's a full stop, and you're going to be used from part A, and you solve for s, and that gives you the distance after it comes to a rest. And that's it for this